So we're asked to find the settling time, rise time, and percent overshoot for the output speed of the motor when a 10 volt input is applied. So we're going to need to find the transfer function that relates together the input and the output. So the output we just said here was the speed of the shaft, so along here, and the input is the voltage to the motor, which is EA. So we need to solve for the transfer function, which I'll call G. It's going to be omega m divided by EA. Okay. So what I might do is draw a few things on this diagram. So one of the things we're going to need is Tm, and that's the torque applied at the output of the motor onto the shaft. And I'm also going to mark in, I'm going to call it theta m. This is the angle of the shaft. So if we have the angular position and we take a derivative of it with respect to time, we end up with the angular velocity, which is this omega m up here in the transfer function. So we need to go ahead and get this transfer function. The first thing I'm going to do is look at what's happening inside the circuit here, and I should be able to apply the equation that the sum of the voltages in that circuit is equal to 0. So EA is going to be an input voltage. We're then going to drop across the resistor, and to work out how much we drop, we need to know the current in the circuit, which I'll call IA. And we're also going to drop across the actual motor, and we're going to call that VB for the back EMF. So let's go ahead and fill in this equation. So I'm going to make EA positive since it's going into the circuit, and this one is going to be negative because it's being dropped across the resistor. And we know that the voltage across the resistor is equal to the resistance times the current. And then across the motor, we're dropping this VB. And that all has to be equal to 0. So the next step for this is to substitute in our Modak constant equations. And then we should be able to eliminate IA and VB from this equation. So we have the two equations. The first one is that Tm is equal to KT IA. Tm is of course this one here, the torque applied at the output of the motor. KT is the torque constant, and we're given its number in the question. And IA again is that current through the circuit. So the other equation is that VB is equal to KB times theta dot m. KB is the back EMF constant, and theta dot m is the rate of change of the position of this shaft, in other words, the angular velocity. So what I want to do is I'm going to rearrange this equation here so that I can substitute it in and eliminate the current. So rearranging, we get this. And for this one, I need to Laplace transform it to get rid of the dot. So it's just going to become VB, alright, goes to itself, it's a function of time. KB is a constant, so it stays out the front. And this one, we know theta m is a function of time, so when we Laplace transform it, we get 1 dot turns into 1s, and we just repeat the variable on the end. So now we want to substitute both of these equations back into the one that we started with. So we're going to get EA minus R. Now this gets replaced, and VB gets replaced. Alright, so we're part of the way there. The next thing that we need to do is relate into the system what's happening in terms of the actual rotational bit of our motor. So in order to do that, we need to draw ourselves a free body diagram, and we're going to then develop an equation of motion that has Tm in it, and that should then be able to be substituted into this equation, and we'll have eliminated Tm. So that's the plan. So drawing the free body diagram of our shaft, this is just a 1 degree of freedom system for the shaft here. So it's just this piece for the mass, or the inertia part, connected to a damper. So we're going to have Tm applied in the, clockwise direction. Let's put that in. And if I'm applying my torque that direction, I would expect the inertia to go that way as well. So that'll be j theta double dot. And then on the end, we also have this damper, which is going to try and oppose the motion. So it's going to be going back the other way, like so. And it's proportional to the speed of the shaft. We don't need to take the difference here because we can see that it's connected directly to a wall, which isn't going to move. So let's go ahead and develop our equation of motion. Whoops. Let's try that again. J double dot. Alright, I'm going to treat this direction as being positive. So Tm is going to be in the positive direction. This one here is in the negative direction. And my inertia term here relates to the other side, and it's in the positive direction. So it's positive in the equation. Alright, now what I want to do is I'm going to put everything with thetas on one side and everything without on the other. So Tm can stay here, and let's just move the damper term across. And now I'm going to take my Laplace transform so that I get rid of these derivatives with respect to time. So Tm just becomes itself. J is a constant, and it gets multiplied by theta m. The dots disappear and become s squared. And theta m again stays, and the dot becomes 1s. Last step is I'm just going to, oh, maybe I'll just leave it like that actually, and we'll sub it in to our equation. So this here was where we got to. We're now going to sub Tm in. So we're going to get R on KT. This is going to be subbed out. And we've still got this other term on the end. Alright, so remember we're aiming for omega m divided by EA. So as an intermediate step, I want to try and rearrange this for the position theta m divided by EA. And I should be able to do that if I factorize out theta m. So each of my terms is going to have one of them. So when I factorize out theta m here, I'm going to be left with R on KT, and also this J s squared. I'm going to take out theta m, so I'm going to be left with R on KT. I'm going to have a D on the top line, and S. And taking out theta m again, this time I've got a negative as well, so inside the bracket it should be a plus. KBS is equal to 0. So I'm going to get E8 equals, and I'm going to shift this all to the other side. So RJ on KT S squared. Oh, I've dropped my plus in here. And I've got RD on KT plus KB. That's all multiplied by S. Oh my gosh, that was meant to be a K. Alright, so, not equals 0 on the end either. So all I've done is I've taken all of this to the other side of the equation, and at the same time I've put the two S terms together. So I should now be able to rearrange this for theta m on EA. And that's what I end up with. So, remembering back to the beginning, what I was actually looking for was the speed of the shaft, omega m, rather than the position of the shaft, which was theta m. So conveniently, both of these properties are related together. So theta dot m is the same as omega m. And if we Laplace transform this, it's the same as theta ms. So all I need to do is, if I multiply both sides of the equation here by s, I'm going to end up with what I wanted. Okay? So at this line I've got theta m times s, which we just said was equal to omega m. EA stays the same. And here I'm multiplying everything by S. So these are going to end up cancelling with each other, and one of these S's disappears as well. Alright, so that ends up being the transfer function omega m on EA that I was looking for. So this question didn't just ask me for the transfer function though, it wanted me to find the time response properties, so the rise time, the settling time, and the overshoot. So what we need to do is put some numbers in to make that possible. And we were given a whole bunch of numbers in the original question. So we're given the resistance, the inertia, and the damping. So what I'm going to do is substitute all of those values into this transfer function. So omega m on EA. So if you substitute in that R is equal to 6, J is equal to 5, and we were given KT as well, it was 2.08. This comes to 14.42. Same thing here, substituting all these values, and we were given KB as well, it was 0.48. This comes to 9.13. So what I want to do is actually obtain my characteristic equation. And for that, I need the number in front of the highest power of S to be the number 1. So if I divide top and bottom lines by 14.42, okay, that's what I'm doing here. So on the top line, I'm going to get 1 on 14.42, which is equal to 0.0693. And on the bottom line, if I get 14.42 divided by 14.42, that's going to just leave me with S. And then I'm going to get 9.13 divided by 14.42, and this leaves me with 0.6333. So we can see this is now my characteristic equation because I have a 1 in front of the S on the bottom line. So now that we see that, alright, this is going to be a first order system. Okay, so it's a first order system because the highest power of S as well is equal to a 1. So that means that we need to use the first order equations for the time response, and those were discussed in the recap video. So I'm just going to pull them from there. So let's write out our characteristic equation, the first order one. So we've got that it's S plus 0.6333, but the general form of it is S plus A. So we can see straight up that this is directly equal to this. So A equals 0.6333. Now we know that for a first order system, the time response is governed by the parameter tau, which is the time constant. And we can get it from our characteristic equation because it's equal to 1 on A. So if you work it out, tau is about 1.579. So now we just need to use this to get each of the different properties we're looking for. So if we start with, say, the settling time, it's an approximate equation. It's approximately equal to 4 times that time constant tau. So if you sub that in, we end up with a time of 6.316 seconds. So that's one answer we were looking for. We can also get the rise time. It's 2.2 times tau. So again, just subbing in. This one comes out to about 3.474 seconds. And the last thing that it asked us was for the percent overshoot. And first order systems do not ever overshoot. So the answer is always going to be 0. Alright, so let's have a look at what this actually looks like in terms of if we plot it. So I've decided to go ahead and plot it in Matlab, and this is the script that I've written for it. So this is just assigning the different values to each of the constants. This is setting up the transfer function, and this part is actually the transfer function. And then the last line is just applying a step input, which is that 10 volts, which is why you see a 10 here. So I've then plotted it and run the script, and this is what comes out. So time is on the x-axis, and the amplitude or the output of our response is on the y-axis. And this, of course, is the speed for our question. So what we can do is have a look at the actual properties of our system. So on Matlab, it's quite handy. If you right-click once you've plotted it, you can pick up each of the different kind of key points. So if we look at the settling time one, what it should do is put a little point down for us. And if you click on it, it will tell you what it thinks it is. So settling time is 6.18 for our system. If we jump back to what we had before, we had that it was 6.3 approximately seconds. But remember, this is an approximation formula, so that's why it's not exact. So now let's have a look at some other things. So we also have the rise time. So again, we can click on that. And it tells us that the rise time for this system is about 3.47 seconds. If we jump back here, we can see that we also calculated that for the system. And the other thing is the overshoot, which you can get from the peak response here. So for a first order system, the peak response is going to happen at time equals infinity because it's never going to overshoot. And then you can confirm that. It tells you that the overshoot is in fact 0%. So that's all we've got for this video, and I'll see you in another one.